So today we're going to talk about mutual inductance. And to talk about it, I am going to perform a simulation using the Ansoft Maxwell software. Before going to the simulation itself, I would like to move forward to some theory background in order to understand the phenomenon that is happening in the coils. So let's move forward to the theory before getting started to the simulation. You can always follow the timestamp below the video in order to go to the parts you would like to watch. So let's go to the theory right now. Okay, so before getting into the theory itself, let's talk about a little bit of the discovery of the mutual inductance, which was found by some physicists, one of them, the American physicist Joseph Henry, in which the inductance was named after him as a Henry. So 1 Henry means the inductance SI unit for the inductance itself. And it's also 1 Webb per ampere, and it goes on as you can read it right there. So here you can see an image, and it was taken from the Sears and Zemansky book 2012, chapter 30, if I'm not wrong. You can check that out there. Essentially, you have 2 coils, the bigger one and the small one. I'm calling the bigger one the coil 1 and the small one the coil 2. It's not the same representation as in the simulation we are about to proceed, but it is quite the same theory that's going on. That's why I'm getting into details in this image right here. So imagine there's this current going through the coil 1. This current is going to create a magnetic field. That magnetic field is going to create a magnetic flux on the second coil, the smaller one. And if you change the current in the bigger coil, that's going to change the flux in the second coil. And according to Faraday's law, that is going to create an EMF on the second coil. So the variation of the flux creates an EMF. That's the Faraday law. So in this representation here, I'm calling the flux in the second coil phi B2. So looking through a logical perspective, there's this magnetic field being created by the current in the first coil. So essentially, this magnetic field is proportional to the current in the coil. So the coil creates a magnetic field, and there's a proportionality between them. So if that magnetic field is creating a magnetic flux on the second coil, there's going to be a proportionality between the magnetic field and the magnetic flux. So by changing the current, you also change the magnetic flux on the second coil, and that's what's happening. So you have a proportionality between the magnetic current on the first coil, the magnetic field created by this coil, and the magnetic flux on the second coil. They are all related to one another. So a change in the first current is going to change the magnetic flux on the second coil, and that's what the Faraday's law is saying right here. So according to Faraday's law, you have this EMF being created in the second coil, and that creation is due to the variation of the flux, which is created by the variation of the current in the first coil. And there's this N2 in this equation there, and it's essentially the numbers of turns in which the coil has, because that is going to influence the amount of EMF created. So remember I mentioned this proportionality between the current in the first coil and the flux in the second coil. Since the number of turns in the coil is directly proportional to the amount of the EMF created, we can also include that in the proportionality that we would like to achieve. And it's conveniently to represent this proportionality as the number of turns, in which we're calling here the second coil, times the flux in the second coil created by the current in the first one. And that's equal to M21. I'm not getting into details what this M is right now. Just in a bit, I'm going to talk about it. And the current in the first coil. And this M21 is the proportionality constant we put in this equation in order to balance it. And this proportionality constant is the mutual inductance. So when you're calling a mutual inductance of a coil, this is the constant you're looking for. And let's talk about it a little bit further. So let's talk about what this means. So you have a constant that relates the amount of turns a coil has, the magnetic flux in this coil, and a current in another coil. So you're relating 2 different coils. or two different conductors that are close to one another in order to influence themselves. This M, mutual inductance, is relating these two events, the magnetic flux and the current. So without getting into details of the environment surrounding the coils, so I'm talking about vacuum right now. This is going to, the M is only going to be influenced by the size of the coil, the distance between the two coils, the amount of spins these two coils had, and the amount of current in it. If I'm not wrong, that's all the eventualities that's going to affect in it. If you're talking about an environment with air or other materials that are surrounding it, you of course will have the influence of the material around it, because the material around the coil, in which can be the air, is going to directly influence the magnetic field, thus the magnetic flux in the second coil. So about the mutual inductance itself, I just put the M in one side and the other parts of the equation in the other side. So the mutual inductance is going to relate the number of spins of the coil in which you're calculating that inductance, the coil 2, the flux in that coil divided by the current in the other coil. And since it's a mutual logical phenomenon happening, you have the same thing with the coil 1. So the mutual inductance is the coil 2 created by the coil 1 is the same inductance as the coil 1 in the coil 1 created by the coil 2. And that's what you have here in this equation. This is the same number for both of them. And you also have a phenomenon that is called the self-inductance. So imagine if you're having this current going through a coil, the coil has a number of spins, and by the time the current's going through one of these spins, it's changing, and it's changing the magnetic field around it, and it's changing the magnetic flux around it. And because of that, it's going to create an inductance in the coil itself, and that's called the self-inductance. It has the same physical phenomenon as the mutual inductance. We only change the letter to represent it, and it's called by L, and that's what we have here. So it's really important to know those two mutual inductance and self-inductance meaning, and what the physical meaning of it is as well. So it's a matter of determining the amount of the inductance that is going between them. And when I say inductance, I'm basically saying that it is a factor that is going to tell you how strong the inductance is going to be. And for that, I would like to only say something here right now. The simulation we are about to proceed, we are not considering the variation of the current into the two coils. The reason why we are not considering that is because we are doing an electromagnetic solution type on Ansoft Maxwell. So that solution type is not going to change the amount of current going through the coil itself. So we will only be able to calculate the mutual inductance and the self-inductance, but we are not generating any, and when I say any, it's any at all, EMF. No matter how big the current is going to be, if you do not change the current in it, by change I mean a gradual change through time, you're not going to create an EMF. You're not going to induce an EMF, because the derivative of the flux through time is going to be 0. So here we are only calculating these constants. They do not depend on the variation of the flux. They only depend on the flux itself. And we can take the mean flux, which is the flux when the flux itself when the current is constant. So that's what we are going to do. So when you have the Faraday's law, applying an idea that if you have a change of flux through time, you're going to create an EMF, that's not what we are seeing in this simulation here. Although in real life, you can do that to create voltage and do some industrial application itself. In order to make the system easier to apply and the simulation easier to apply as well, I'm doing it in the electromagnetic static solution type on Ansoft Maxwell. So let's move forward to the simulation itself. So moving forward to the simulation itself, I just named it. I study in this university here in Brazil, so everything you're going to see here is properly named in Portuguese, but I'm going to apply the names into the simulation in English to help everybody else that do not speak Portuguese language. So let's move forward to the simulation right now. Okay, so here we are in the Maxwell software view. The first thing we like to do is to create a 3D design. So by creating a 3D design, you get into this 3D view here. You have the three axes naturally. And let's move forward to the coils itself. You could draw a coil using this draw box here. It's quite hard to do, and thanks to Ansoft Maxwell, they already created a primitive to do it since it's a quite common shape. So you go here to user defined primitive on draw, slab, segmented helix, polygon helix. Right here, I have a video explaining how to do a coil already, and also the conduction path in which I'm introducing in this video as well. You can check that out right here. But essentially, I'm going to go through it a bit faster than I in the other video, and you can check that out over there. If you have any doubts, you can also comment here in this video. So I want the polygons being segmented into 8 vertices. That's going to make the solution easier numerically and software speaking. I'm starting the helix radius for this first coil to be 10. I'm going to radius change in a bit, and I don't want any pitch. So since I'm not putting any pitch, it's not going to extrude in the z direction. It's going to remain in a plane. This plane being the x and y plane. And the radius change, I want it to be, it has to be at least 2 times the polygonal radius. Of course, if you want to change the radius through each turn, you gotta have the turns to do not collide to one another. So you have to have the radius change to be higher than the polygon radius itself. So let's do it, a diameter itself. So let's do it. The radius change here, I'm going to put a 2.5, and the number of turns, let's say 20. Why not? Segmenters per turn, 36, which is going to split each turn into 36 segments, in which creates a better solution. So creating the coil, it's going to take a little bit. Nice, so I have the coil here. It has 20 turns, in which for each turn, it's increasing its radius by a length of 2.5 millimeters. Okay, so here we have the coil created. So I want to do another coil, and that's what we're going to do now. We go to the same idea, draw, slab, segmented helix, polygonal helix, and we create another coil. So the idea here is that by creating another coil, we represent what we did in the theory background. We want to create a mutual inductance between them. So polygonal segments, I want 8 as the first one, and I already explained that. I'm gonna leave the helix radius to be the same, so it has the same first helix radius, and I want no pitch as well. Changing the radius as 2.5 as well, and the number of turns I want it to be half as this. That's the one in the bottom, as the one created, and I'm leaving it as it is for the other parts. So right now it's going to create it, and I see you in a bit. Okay, so here we have the coils created. We have the 2 coils here, they're intersecting one another. So if you see in this normal view, you will only see like one coil because the other one is right here, is intersecting with the other one. And since they have the same parameters, but the number of turns, they're going to be like as one if they're not different, in any other way. So what I'm going to do now is to extrude it in the z direction. But before doing that, I want to create something called a parameter. And the idea behind that is if you want to do a procedure in which you want to create number of steps and see the difference between these steps in the simulation, you like to want a variable that is there for you to use every single time. And you want to create a variable, and this variable is going to be one of which as a length, and that's what I'm doing now. So I go into the project itself and do that. So here I want it to be a value, and I'm adding it. The name, I'm going to call it distance, and the unit type is going to be length. So just press L, it already has length here. I'm leaving the units as millimeters, and the value here, it's predefined by the user, which is you. I'm choosing, let's say, not 15, let's put like something as 25 millimeters. That's a good number. So let's move forward, and okay. So here you have this distance value right here. It's a variable that's going to be there for you if you want to use it during your simulation. So now what I want to do is to extrude the coil, the small coil, in the z direction. You could do that by creating a coordinate system in the z axis only, and then setting the orientation to that coordinate system. I don't want to do that. I want to move. And by choosing to move, I could do it as in the distance I just created. So let's set it everything as 0 or just like that. Yeah, so I created the move as default, so it has like 0, 0, 0 here, but what I want to do is to put the variable I created in the z-axis. So it has like this character here and then distance. Is it wrong? Distance, all right. And it's moving right there to the distance value. Okay, so here we are. You can already see that it was extruded in the z direction, and then you can see the difference between them. So now we have two coils. Oh, let's proceed to the simulation. No, you cannot proceed to the simulation now. Remember, you have to have currents going through them. And in order to do that, it's not only to click on them and assign a current itself. The software needs to know where that current is going through, and it also has this phenomenon that in the Ansoft Maxwell magnetic static solution type, you gotta have something called the conduction path. And essentially, the conduction path is a path, a wire that is going to link the material you want to have the current going through and the boundary around it. So when you assign a boundary to the geometry you are creating and you wanted to assign a current to that geometry, you need to have a conduction path touching that boundary. Or you could have the geometry touching the boundary and assign the current to that geometry without having any conduction path. But here in this way, how am I going to put like this end of the coil right here? You see there's an end here to the boundary. It's impossible without a conduction path. I'm going to show you right now why it's impossible. So creating a region here, just as an example, is going to touch every single outside faces of it. And you see, the region is not touching the faces here inside of the place in which I want to have one of the wires. And we need to have a conduction path in order to this wire here touch this region there. So let's do that right now. I'm just going to leave the region as it is, and I can change the parameters later. I'm only doing something here in which is hiding this view. Okay, so let's move forward and do the conduction paths. I'm going to do only one of the conduction paths here, as we have two coils and both of them needs two ways ins and outs for the current. We have to have 4 conduction paths here. I'm doing one and speeding the video up in order to make the video shorter. And that's what I'm going to do now, teach you how to do one, and then we move forward to the other ones. So what we want to do here is we want to, we want to go to one of the coil ends right here and do a line. So by drawing a line, you're going to orient your conduction path. So you want to choose right the center of it. It has to be right in the center of it, which, if I'm not wrong, is right here. So by choosing here, as a design idea, I wanted to go into that direction. You can see the x-axis right here. So I want to go that coil to be going to that conduction path to be going to the x-axis. I don't want to go straight to the x-axis because it's going to be weird in the design I'm creating. So I'm going a bit into the negative y direction, a bit on the z direction, then going to the x direction. It has to go through the z direction in order to go through the other coils here. Since they are in the same plane, I cannot go straight forward into the x-axis. I have to go a little bit further or below in order to go to the x-axis, naturally. So let's do it. So I'm creating a line here. I'm not specifying any directions now. I'm just creating for creating and doing 1, 2, and 3. That's all we need. So for now, we have the line created. It changes to this weird view here, but we can go to the lines itself. So we have the one line here, the other one here, and the other one here. You can see it turns black when I click it. You see? All right. So the first one I wanted to go to the minus y direction, as I said. So you go here, and the point 1 and point 2 represent where the line starts and ends. I wanted to have the same ending and starting point, but changing one of the axes. And the axis I want to change is the y-axis, naturally. So doing that, as it is going to the negative y-axis, that's what I want. So here's okay. And it changed a little bit to the minus y direction. Doing the same thing with the other one, but changing only in the Z direction. That's what I'm doing right now. And I want to change a bit longer than the length of the segmented polygonal helix radius I created. So let's put it as 28. So it's going up by a factor, by a value of 3 millimeters. That's what I want as well. And now I want only the line to go into the Z direction. So let's do the same thing here, copy and paste the initial part of the line and the end part of the line, and only change in the x-axis. And that I'm going to put it as 100. So now we have the line created. You can see it right here. So look, the line is going in that direction there. That's what we want. We're going to do the same thing with each one of the lines, and that's what we want. And by doing that, we are going to have all of the lines touching the faces we want. I'm going to accelerate the video here and do the other ones. But before doing that, let's name the lines. So this first one, I want to name it as the, let's say like the small coil. So it's going to be small coil 1. Okay, and that's what we're calling it. So by choosing small coil here, we go to the helix that is the small coil, and we give the same name for it without the 1. Okay, so by doing that, it's going to be easier to understand. I'm doing the same thing here, changing names for those ones as well. So this one is going to be big coil. I'm keeping names as simple as possible for your understanding. And so here we are. We have one line. Let's do the other ones. But before that, you have the line here. I wanted to make it as a conduction path. Right now, it's only a line. So you go into create polyline and type. You choose the type of your geometry you want for the conduction path. Right here, I'm choosing the rectangular one. And I want to give it some width and some height. So width 1.2 and height 1.2 as well. You can choose the amount of height and width you want, as long as it is smaller than the geometry you created here for the coil. Okay, so you can see right here, it is touching the center of it and it's connecting it, and that's good. So that's the coil. It's not a perfect circular shaped coil, but it's enough. That's what we want. So now I'm going to accelerate the video for the other ones. Okay, so here we have the conduction paths created. So remember we did a region here. Since the conduction path went through the region, it was deleted automatically. I created the ones in the bottom part here, and I didn't change their names. I named it the big coil as big coil, and I'm changing the names of the polylines to it as well. Just copying and pasting it. It's going to name to put a number to it as well. So that's what I'm going to do right here. And this is going to be naturally the second one as well. Oh no, the region is here. My bad, it wasn't deleted. So I have the region here, and it is touching the faces I want. But look, it is there. Let's check it better right here. Just a second. I remember I hided it, right? So now let's show it. You can see as the line here, the red one. And I want to see what is happening inside this region. This region is going to be where the simulation is going to be calculated. So I wanted to look what is going on inside of it. But look, it is quite close, actually intersecting with the tangent of this coil here. And I don't want that. I want to see what's going next to it as well. The region of influence has to be bigger. So in order to do that, let's create a region. And I double click in it, create a region. You can go here as well. And then I want to put some offset into the directions I want. I do not want to change the positive x direction because I need the conduction paths to be touching it. So I'm not changing the x direction plus x direction. I'm only changing the minus x direction and the other directions as well. So here I'm going to put 25. That's going to create an offset of 25% of the amount of size we have already. The y and the z directions, I'm going to put it as, let's say, 40 for all of them. That's enough for what we want here. Okay, just a second. 40 here and 40 there. Okay, everything is 40. So here the region is bigger. So that's what we want. It is bigger here in the z direction as well. Good. Actually, look, I want to put a bit of a bigger sizing here in the z direction. Let's put 100. And here as well. Good. So now we have the region here, and we want to move forward with the solution. Before going to the solution itself, let's change a little bit of what's going here. Remember in the first part of the video in which I mentioned doing this coil, in which you have this parameter called distance. So that's for parametric simulation. I'm not doing the parametric simulation here, but I'm showing you the steps to do it. And the idea is that by doing that, you have this distance that is going to change. It's a variable. It's now named after 15 millimeters, but it can change to the amount of millimeters you want as long as not intersecting with the coil. But the idea behind it is that you want the coils to be together with the conduction paths of it. It has to be united in order to move everything as one. So to do that, I'm choosing all of them that are represented in the same coil and doing this Boolean operation called unite. You can go here and do the Boolean operation here as well. If I'm not wrong, it's here, modular Boolean, and do the unite one, or you can click it right here. So unite the first one, and then you do the same thing with the other one below, and unite them as well. So by doing that, they're going to move as one if you do a parametric solution here. Okay, so now we go into the design and we want to put some excitation. So this is the most important part for it, because now it's where you are doing a current to be going through the coil. So you want to choose the current to be touching a face. That's the only way the magnetic static solution type understand a current being applied in the way I'm doing right here. So assign excitation, put a current, and let's say just like current 1, and give it a value of, let's say, what, 3 millimeters. Okay, and the other one in the other face, it has to go in and out. Current, right? Yeah, 3 as well. But look, the arrow here is pointing at the same direction as the first arrow. We don't want that. We want to swap the direction of it in order to go in and out. Okay, so here we have the first current, and let's do the same with the other ones. I'm leaving the same currents for them as well. So current 1, 3, here as well. Swap directions, good. Very nice. So now we have the current, and okay. So now that we have the conduction paths created and we have the region expanded as well, we want to assign the materials to our coil. The materials we want to choose here is the copper. So let's do that. Assign material, go to copper. Very nice. So we have copper here, press OK. And now that we have a copper and the other material to be as vacuum, which is the region, we go to the parameters here. We want to create a matrix. So we assign a matrix here and we choose both of the currents there. The idea here is that by creating a matrix, we can relate the inductance and the mutual, the self and the mutual inductance after the results. Okay, so now I have the matrix created, and then I just press like to include the current 1 and 3. You have them there. So that's going to correlate the currents here in the solution. Now that we have everything created, the matrix, the excitation, and the region around the coil, and the material to the coil, let's validate and see if everything is okay. It's going to ask for a setup, but before that, let's just see if everything is checking. Okay, so we see that it's only asking for the analysis setup, and that's what we're going to do now. We set up right here, solution setup, leave as default, and then okay. Now that we have everything done, we can move forward to the simulation itself. It's going to take a little bit, so I see you in a second. Right, so now that the simulation is complete, we can move forward to the results. The simulation took about 30 minutes to complete. It went through an amount of 3 adaptive passes, which is an requirement of the magnetic static solution type, in which it refines the mesh and the solution for each one of these passes. And now that we have the results, let's check it out. So remember in the theory, we mentioned this thing called the mutual inductance and the self-inductance. So that's what we want to calculate. When we created the matrix between the two currents, for the two currents, we get this. By clicking results, we can go to create magnetic static report, go to data table, and choose what we want. So I want to look to the inductance created here. So if we go to L, which is the inductance, we can see here that there's this induction between current 1, which is a self-induction. We can go through the current 1 and 3, which is the mutual inductance. And we don't have to go to the 3 and 1 because as seen in the theory, both this and this one, the current 1 and current 3, they are the same. And then we can go to the current 3 and current 3 inductance as well. And we create a new report. So now we have here the inductance created. And look, for the self-inductance here, in this, if I'm not wrong, is the second coil, the upper coil. We have this number here of this Henry 4.123 U Henry, which is a very small amount of inductance, but that's what we're looking for if we take the amount of amperes disposed and the geometry and the size and the distance between them. And for the mutual inductance here, we have this other value here that is even smaller, and the self-inductance for the bigger coil, you can see that it's bigger as well because you have a bigger amount of turns in it, so you have a bigger amount of the mutual inductance in it as well, even though it has the same current. So this is what we are looking for, and this is the results you get here. So remember when I mentioned if you wanted to create a parametric study, you can go through these results here and then create a data table for a lot of distance here related to the variable we created here, distance. And I'm not doing it here, but you can do it. It's just to show you that it is possible to do. So you change the distance in the parametric static and it is done there. And now we can also see the fields overlays here. I'm choosing the planes, so let's choose the XY plane and then put some field overlay so we can see the both magnetic magnitude and magnetic vectors going through here. So what we want to see is, I'm choosing in the region so we can see it better. So what we want to see is where the magnetic field is higher and where it's not that big, in order to understand if the phenomenon is representing the reality. So here we have. So the plane created was right in the X and Y plane. We can animate it so we can go up through the Z axis here. But for this, we can already see that there's this amount of magnetic field here, which is the biggest on all this plane. And as long as we go up, you're gonna see these changes. And that's what we have. So we have the magnetic field like being stronger here in the center. So let's put some animation as well so we can see a little bit of what's going on. I'm putting some steps here so we can see the plane going a bit slower. Normalized distance, with which is the distance we chose. You can choose the distance that we defined it as a parameter, but that's not what I'm going to do here. Okay, it's creating the frames and we will have the animation in a bit. Good. So if we slow it a little bit, you can see like how it gets stronger when you go through the coils and it dissipates into this minimum amount of magnetic field. That's what we have here. We have the inductance. We have the magnetic field going to get bigger in the center of it, and that's what we want. And okay, so now that we have this, let's move forward to the vectors as well. We can choose the same plane and go to field overlays and see the vectors as well. Choose the region as well. And by choosing the region, you're going to see the vector around this region, okay? So you're going to see the vectors created by the coils around the region defined. And just by changing this, I don't want to see the magnetic plane, I just want to see the magnetic field and do some animation here as well. So we can do the same normalized animation with the same amount of steps, which is that one I clicked it. I don't have to create another one since it's going to be in the same normalized distance. So it's creating, and now you can see the magnetic vectors going through. It's a quite nice view, and you see how present the reality. If you look into the theory of how magnetic fields are disposed into coils, you're going to see represent the reality as well, which validates our problem. And okay, that's what we have here. And thank you very much. The idea behind this video was to show how to get the mutual and self-inductance, which is what we got there. So thank you very much. See you next time.